Okay, good morning, everybody. Welcome to week 6. I kind of picked up a cold over the weekend, so those of you in person, I will not get too close to you today, I promise. I'll kind of try and stay up here a little bit, but I hope everybody enjoyed their nice long weekend. I emailed you your notes for week 6, and then if you're in person, I also gave them to you in person. So we're focusing on 2.03 and 2.04 today, which is exponential functions and then growth and decay. So our agenda is to do those two sections together, and then anyone who showed up in person is also going to get a midterm review. So whether you are at home or in person, your week 6 essential question, it's asking you to solve a question later in today's session, so you just have to stay tuned to know which answer to submit. So those of you in person, you'll still be solving the question as well, but I'm going to let you do that in Teams today. Okay, so let's jump right into 203. The big ideas, these are kind of what I want to make sure you really know how to do before you leave my session today, is when we're graphing exponential functions, how do we graph them? And what do we know about how A, H, and K shifts our graphs? So if you're able to answer those two questions by the end of today's session, you are in perfect shape and you know exactly what I wanted you to accomplish. So how do we graph? So turn to this page in your notes because I give you a coordinate plane. And I have this function here. And it's an exponential function because my variable is an exponent. So this is new for us. We are used to graphing x squared, x cubed, but we've never actually had my variable as the exponent. So you guys see how this one's different, right? This time my variable is the one that's the exponent. So how am I going to graph those? We're going to start by always making a table. No matter what kind of graph you need to make, you can always fall back on making a table. So here we go. Let's make a table of values. We're just going to pick some and we're going to try them out, and we're going to be able to do a quick sketch of my graph. Because on the test might say, which one is the graph of f of x equals 3 times 2 to the x? How are you going to know which one's the right graph? You're going to make a quick little table, and then we'll be able to sketch a couple key points on my graph. Let's pick some values. What would you guys say is the absolute easiest value to plug in always? 1. Okay, 1 is pretty easy. I think there's 1 even easier than 1. 0. So I'm for sure always going to pick 1 and 0 because those are super simple to plug in. So in my t-table, just remember your first column are your x's, your second column are your y's. So let's come up here to my function, and we're going to plug in a 0 and a 1. So first time it's going to be 3 times 2 to the 1. And then when I plug in 0, it will be 3 times 2 to the 0. So let's work out what each of these are. Let me grab my pointer finger. So all I did was I rewrote my function, and where I had my x, the first time I'm plugging in a 1, the second time I'm plugging in a 0. Is everybody okay with that? Why do I have this under the y column? Because what's another way to label f of x? Y equals. Good job. So this is actually the same as saying y equals. So it's just called function notation. That's why they're using the f. It's just a new vocabulary word for something you guys have been doing for a really long time. So let's try plugging in the 1. So this would be 3 times 2 to the first. 2 to the first is just 2. So that really is 3 times 2. And what's 3 times 2? 6. So when I plugged in a 1, I got 6. Remember, when I'm doing these, I have to remember order of operations. So I have to do my exponents before I do my multiplication. You guys okay with that? Exponent first, multiplication second. So down here, I have this 2 to the 0 power. Anybody remember from the past what anything to the 0 power is? It's not 0. It's actually a 1. So anything to the 0 power, the 2 to the 0 becomes a 1. So I'm going to get 3. So let's plug in these two numbers. These are just coordinates, correct? I have my x coordinate and my y coordinate. So plot 1, 6, and then plot 0, 3. So we already have two spots on my graph. I'm sort of getting an idea of what my graph's going to look like, but I need a couple more points to really get a good feel for what that graph is going to look like. So I tried 1, I tried 0, let's try 2. So I'm going to do 3 times 2 squared. We'll do our exponent first, so 2 squared is 4, and 3 times 4 gives me 12. So 2 comma 12 is going to be another point. So if I look on my graph, that's going to be way off my graph. 2 comma 12 is going to be way, way, way up there, way up high. So I don't really need to pick any more numbers to the right because they're all going to be really, really high. What other numbers should I try for my table now? I need something over to the left. So let's try a -1. So I'm going to do, oops, that should be a 3. So 3 times 2 to the -1. When we have negative exponents, let's remind ourselves what we do with that. I can't have a negative exponent, so instead I have to move it to the denominator. So it's going to go on the bottom and become a positive. So that really says 3 times 1 over 2 to the first power, which is 3 times 1/2, which is 3 over 2, which we know is the same as 1/2. So at -1, I'm going to get 1/2. Did that thing about the negative exponents ring a bell? Does that kind of come back to us a little bit? When you have a negative exponent, you just have to move it to the bottom. We're going to try one more. We're going to try -2. So 3 times 2 to the -2. I can't have a negative exponent, so I'm going to move it to the bottom. And once we move it to the bottom, it becomes a positive. So right now I'm at the 1 over 2 squared. So that's really the same as 3 times 1/4, which is 3/4. So at -2, I'm going to go up 3/4. So are we seeing that this is actually a decay function because it's decreasing? No, actually I said that backwards. This is a growth function because remember we always read graphs left to right. So as I start at the left and I go to the right, it's going up. So this would be a growth function. But at first it can look tricky. It looks like it's sloping way, way down. So just remember we always read graphs left to right. This is going to get really, 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 really close to 0 but never past 0. Now how do I know it's never going to pass 0? Because I'm never going to get a negative. Think about why I'm never going to get a negative. When I plug in negative numbers, they just become fractions, positive fractions. So no matter what number you can pick for x, I'm going to end up with a positive answer. Does that make sense? What happens when I put in a negative? Just becomes a fraction. What happens when I put in a positive? I get really humongous numbers. So no matter what I pick, I'm never going to get a negative in there. So it's going to get really, really close to 0 and never, ever pass it. So domain. Domain are your x values. Does your graph go to the left? Yes. Does your graph go to the right? Yes. So your domain, we're going to say, is all reals. The other way that they might say it is -infinity to +infinity. That's another way to say your domain. I mean, it goes all the way to the left, all the way to the right. And I know you may be thinking, but it slopes up really, really high on that axis right there. How is that going to go all the way to the right? Well, if you keep picking humongous numbers, eventually it's going to keep on going, 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 eventually. Now range are your y values. So range we have to look up and down. Does my graph go up? Yes. Does my graph go down? No. So my range is not all reals. At what point does my range stop? At what value? What value does it not cross right here? 0. So when we're talking range, we're talking y. So I'm going to say y is greater than 0. So let's talk domain and range one more time. So domain are your x's, meaning side to side. Did your graph go left? Yes. Does your graph go right? Yes. All reals. Range is up and down. Did my graph go up? Yes. Did my graph go down? No. Where was the tipping point? 0. It's only the values that were bigger than 0. Now an asymptote, that's going to be an imaginary line that your graph is never ever going to touch. Sometimes we have vertical asymptotes, sometimes we have horizontal asymptotes. So in this case, I'm actually able to draw on a line right here that it's never ever ever going to cross. So the asymptote is y equals 0. Anybody notice anything about your range and your asymptote? Think about that for the next slide. They're almost the same, aren't they? Your range and your asymptote, almost the same. So let's try another one. So here, Carly, if you're at home and you can pull up Desmos.com, you feel free to do that. Our iPads in the room are not connecting to the internet, which is fabulous. Love when that happens. Gotta love technology. So we're going to graph this together using Desmos.com. So for those of you in the room, I'm going to put a graph up for you. So let's do an application share. Okay, and at Desmos.com, we are wanting to graph 4 to the x minus 1. Carly, if you're able to see my screen, my Desmos screen, can you give me a smiley face? All right, fabulous. Okay, so here's 4 to the x minus 1. And I want us to know, let's talk domain and range. So does this graph go to the left? Everybody says yes. Does this graph go to the right? Yes. It goes up. And it goes down a little bit, but it doesn't go all the way down. So let's think about how you're going to define your range. So let me zoom in just a little bit more so we can see exactly what number it's at. So this graph goes up, but what's the tipping point? What number does it never cross on my screen right there? -1. So how am I going to write my range? Y is greater than -1. Can you please add that to your slide? And just do a really quick sketch of this graph for me in your notes. So y is greater than -1 is your range. This graph passes through 0, 0. We're just doing a really quick little sketch for ourselves. Okay, let's talk about asymptotes for a minute. So if my range is y is greater than -1, what would my asymptote be? Y equals -1. Y equals -1. Good job. So are we starting to see a correlation between my asymptote and my range? Okay. Can you pick out why you think it's a -1 without me graphing it? Can you guys look at the equation real fast? What do you notice about the equation? There's a -1 in it. Maybe that's going to relate to my range. Maybe that's going to relate to my asymptote. Okay, so watch this one. This is not in your notes. I'm just going to change this number, and let's see if what we're thinking is the rule holds true. Watch if I change it to a +2. Your range would be y is greater than 2. What's your asymptote? Y equals 2. So it sounds like you guys have come up with a pretty general rule so far, right, about how you can find range, how you can find the asymptote. How can we describe that in my function? It's always the number that is, what do we call that number at the end? Anybody remember? The end number, yes, but it has a vocabulary word. It's called the constant. It's the one without the variable. So, maybe range and my asymptote has something to do with this constant. Let's try another one. Somebody pick a number. Positive, negative, doesn't matter. 6. Positive or negative? Okay, negative 6. I need to zoom out. Let's see if it holds true. So here's negative 5, here's negative 6. So my range would be all real numbers greater than negative 6, and my domain is, my asymptote, y equals negative 6. Good job. Okay, on the next slide in your notes, it says what are the asymptotes of, and I give you this function. Before I draw it on Desmos.com, can you guys write down what you think is going to be the answer before we draw to double check? So we're looking at the one that is 3 times 2 to the x power plus 5. What would be the asymptote? What did you guys guess?
5.
You were right. So y equals 5 would be the asymptote. Good job. If I asked you domain, which I didn't, you would say y is greater than 5. What's your domain? No, domain. Domain are x's. All real numbers. Good job. It's going left, it's going right. So on the quiz for 2.03, you're going to have domain questions, you're going to have range questions, you're going to have asymptote questions. Are you allowed to graph to double check? Yes, you may absolutely graph to double check. That is not cheating. It's using the resources at our disposal. Like I tell students all the time, you don't ever have to memorize a formula, you just have to know how to use them. Because when you guys are in the real world with your jobs, your boss is never going to say, here, do the quadratic formula, but you can't look it up, right? No, you get to use all the resources available to you. You just have to know how to use it. So, okay, great job. Next slide. So let me see now if I can turn off this desktop share. Miss Alvarado taught me the other day. She walked me through it, and for some reason now I'm not able to do it again. Had to do something with this button right here. Hang on one second, Carly. Okay, Carly, can you see my screen again, my PowerPoint? Yay, I figured it out. So we answered these questions already. Now we're on this slide that talks about your exponential functions and what a, h, and k does to the graph. And we briefly talked about this last week. I don't know if you guys remember. It was at the very, very end of our session. And what we said was, whenever you have a number here at the very, very end, that is going to be your vertical shift. So that's what shifts it up and down. Let's think if that makes sense for what we just saw in our last problem. When I added 5, what happened to your graph? It got shifted up 5, didn't it? And my asymptote was at y equals 5. Let's think about this one. When I had the 4 to the x minus 1, that shifted my graph down 1. So that number on the end, not only is it your range, not only is it your asymptote, but that's your vertical shift. That's shifting your graph up and down. So anytime I give you guys a problem, you're able to identify that number really, really quickly now. So let's come back to our formula. So k is always your vertical shift. If I ever put a number in the very, very front of your graph, that's going to be your stretch or your shrink factor. It means it makes it really, really wide or really, really skinny. But then we do have one other kind of a shift, and that's your h. That's your side-to-side shift. But there's something weird about your side-to-side shift. Does anybody remember back from when we did absolute value graphs or parabola graphs? How does it change if it's in the parentheses? If I see a minus h, anybody remember? Let's add this word. It's going to be the opposite of what you see. Meaning, if I see a minus h, that's really going to be shifted to the right. And if I see a plus h, that's going to be shifted to the left. Here's how I had you guys remember it in the past units. Let me give you a quick little example here. And change colors. So remember when we're doing factors, and I say what's really the solution, and we have to do the opposite. You guys remember how I always talk about doing the opposite when it's in parentheses? Guess what? Same rule applies. So when it's in the exponent or when it's in the parentheses, you have to be thinking it's the opposite. It goes in the opposite direction. So let's try one. So if here is my original function, they sometimes call that your parent function. You guys have heard that name before. The parent function is like the very most basic version of the function. And then I'm going to change it into this. I want to know, how is my transformation going to look different than the parent function? Meaning, what does this minus 2 do to your graph? What does this plus 4 do to your graph? So let's all start with the plus 4. The number at the very, very end. What does the number at the very, very end do to your graph? Shifts it up. So we would say that that's a transformation of up 4 units. And how about the negative 2? Be careful. I know I don't have it in parentheses, but it's an exponent. So it's 2 to the right. Good job. 2 units to the right. So if we were to graph my original graph and my new graph, they would look identical, except the second one is shifted to the right 2 and up 4. It's kind of like we used to talk about vertex. You're taking that initial starting point and you're just shifting it a little bit. That's what's happening here. So the number at the very end is your up and down, your vertical. The number inside is left and right, but it's opposite of what you see. So if it's negative, that's going to the right. If it's a positive, that would be going to the left. So I'm going to give you one more to try. Let's do a little line on the slide and try one more. So we'll stick with our original parent graph here, but I'm going to change it slightly for you. Okay, so you guys tell me on your paper, how does this shift your parent function? Describe those steps to me. So really when you're looking, you're identifying 2 points, right? That's all you have to do. You're looking for the number at the very end and the number that's in the exponent. So Taylor, what do you think about the number at the end? Good job. So that's going to move it down 3. And Alex, what do you think about the number inside? Good job, left 3. Because inside the parentheses, it's always opposite of what we see. Great job. You guys did great. So do you have to memorize what A, H, and K does to your graph? No, but by knowing these 2 numbers play key roles, doesn't it make it way easier to answer the question? You don't have to regraph it. You don't have to do anything. Plus, don't I already know what my range would be on this one? My range would be y is greater than negative 3, right? And then y equals negative 3 would be an asymptote. So you know a lot about your graph just by studying them. Okay, now we're going to move into what you're going to see on your midterm. I have 2 sample questions for you here. Yes?
Did we do the Anderson stretch and shrink factor, or were we not supposed to?
Okay, great question. So Billy's asking me, oh, good. So on here, yes, we could technically point out the 1/2 and say that that's your stretch factor. The number that's out in front is just your stretch or shrink factor. What do you guys think would happen if I made it a negative, though? How would that change the way your graphs look? Because right now, haven't my graphs really kind of looked like this or like this? What do you think a negative would do to it?
Probably make it go opposite.
Make it go opposite? Okay. Make it go down? Maybe in the other quadrant, something like this? Okay, you're right. Okay, so as you're experimenting, and I will make sure that these are up and running a little bit later today so we can do some experimenting on them. But as you're adding negatives out in front, it's just going to flip your graph upside down. It's going to make them go in the bottom quadrant. So how do you think that would affect your range, by the way, if I have a negative? Interesting. Let me add a new page here. So let's pretend I have this. I have one that looks like that, which is a negative. So in this case, your range would be y is less than whatever that number happens to be. Okay, so if we do have a negative a value, your graph's going to get flipped upside down, which means that your range gets flipped. Your inequality gets flipped. So you haven't discovered those yet. That's why we didn't practice them, but just to throw that out there that you'll experience a few of those in the homework. So now we're going to do 2 from your midterm. I have taken these exact problems off the midterm so that way you can see the wording. Typically, every question has 3 different options of a question that each student would get. So this was one of the 3 options that I have now removed from the test, just that way you can see exactly what it looks like. So we're going to practice this together. It says a colony of ants has 50,000 members. Sion thinks the colony will grow at a rate of 3.1% each hour. How many ants should he expect there to be in the colony after 10 hours? I don't know if your parents have ever had ants at their house, but it really does feel like they multiply exponentially. Once you see 1, there's like a million more that show up after that. So what we learned this unit is that exponential graphs are not straight lines, right? They curve up really steeply, meaning they keep growing really, really, really fast. So we have to have a formula for that. And the formula, I think, did I leave this on your notes already? I know I took the work off, right? Okay. So here's your formula. You need to know this for the midterm. This one is not given to you. So can you like put a big red star by this formula or put a post-it note on this page? You need this one for your midterm. So as I said before, it's never cheating to look up a formula. It's not. So if you're ever on a test and you're like, gosh, I need to look that formula up in my book, that is just fine. It's not cheating. But if you have it handy, it will save you time. So we're going to try it. So look what it's showing us here. It's going to list what all of the labels are, and then we'll just plug them in. So here we go. So it says B is the initial amount. So where we see B, we're going to put what we started with. R is our rate of growth, and T is our amount of time. So T for time, R for rate, so the letters kind of make sense here. So let's see what we're going to plug in. Let me give you a second to copy that down, and we're going to make sure that that makes sense. And what I do on every quiz and test, even though I've been teaching these same math classes for 13 years, I always write my formula, and right underneath it, I fill in the numbers that belong there. That way I can make sure I did each piece of my puzzle. So B is the initial amount. Looking back at my paragraph, the initial amount was 50,000. Inside my parentheses, I do 1 plus my R. Why do you guys think, even though it said 3.1%, down here they don't have that? Why do you think we do that? Any ideas? Okay. Because calculators cannot do percents. Can you believe that? They can't. So we have to change it into decimal form. How do I go from a percent to a decimal? I move my decimal place 2 spots. 2 spots to the left. So I had to go 1, 2. So 0.031. So just make a note of that. Because if you were to type in 3.1% into your calculator, your calculator can't do that. They don't understand. I know, bizarre, right? And then my time was years, or hours, sorry. So my time is 10 hours. This is just a calculator question. You are absolutely allowed to use them on your quiz and on your midterm. That's totally fine because we don't do things to the 10th power that are decimals in our head. We use calculators for that. But let me give you a couple pieces of advice when you're using a calculator. Do you guys have a phone on you, your cell phone? Can we grab that out and we'll try it? Because the order that you type things in is very important, and I want to make sure that, that you know how. As you guys swipe up your calculator on your phone, if you actually tilt your phone to the right or to the left, it pulls up a scientific calculator. Isn't that kind of cool? Don't know if you knew that was there. You get a scientific calculator when you tip your phone to the side. So the first thing that we're going to do is we try and do all of the work ourselves. That way the calculator does very little work. And what I mean by that is we are going to do this part first. So can you guys add that part together first? You probably don't even need a calculator for that part. Everybody okay with where we're at? All I did was I'm doing as much as I can without the calculator first. So 1 plus 0.031 gives me 1.031. So now in our calculators, we're going to just do this portion first. Why do you think I'm going to do that portion first? Calculator doesn't know order of operations. So if you guys were to type it in from left to right, it's not going to give you the right answer. Your calculator would do 50,000 times the 1.0 and then do the exponent. But is that proper mathematics? No. Proper mathematics is exponent first, then you times by the 50,000. See what I mean? So calculators only know what we tell it. So here we go in our calculators. You're going to type in 1.031. It's usually like an x to the y button, I believe. That's your exponent button. And then you'll hit 10 and enter. Is it your x to the y button on your phone? Oh, you have the hat symbol? Okay, so some calculators have this little hat symbol, which is awesome. Anybody have a different symbol on there? If you can't find it, I can come help you too. Once you have hit enter, now you can say times by 50,000. And let's see what you get. $67,851. Yes, no, maybe so? Yes? Okay. So it's really important that even though you're allowed to use a calculator, calculators are not as smart as we are. Believe it or not. They'll do the hard computation, but they don't know order of operations like we do. They don't understand that. So it's very important the way that we type things in. So here's a question for you guys. How would this equation in my box up here be different for exponential decay? What do you think would be the main difference? This is growth. What would decay be? What do you think, Billy?
It would be lower.
How would this function change? How would this equation change for decay? There's one difference. This is growth. Growth is this. What would decay be? Subtraction. Good job. So let's write that right next to it. So my decay function would be exactly the same, except it would be minus the rate. And then we have one more we're doing together before we stop the recording to work on our midterm review. So if you did not get 67,851, make sure you continue to practice on your calculator until you do get that answer, because that'll show you the proper way to type things in. And I'd be happy to walk around and help with that in a minute. Is everybody okay? Growth has the plus sign, decay has the minus sign. Okay, last kind of question you're going to see on the midterm involves compounded interest. And who doesn't like money, right? You're eventually going to want to buy a car. You're eventually going to maybe be married with kids, have a savings account. Compounded interest is awesome. Basically what that does is it's going to tell you how many times during the year it calculates your interest and adds it to your total. Calculates your interest, adds it to your total. Because as you're accruing interest, your initial investment is growing, 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 growing. So if I start with $100 and every day they're going to give me 2%, that's awesome. Every day they're giving me money. Most banks don't do that. So let's check out this example here. So after 5 years, you guys are going to do an investment and you're going to leave it there for 5 years. What is the total amount of a compound interest investment of $32,000 at 3% interest? So we're going to try this one together. Even though Mr. Bremer's not a math teacher, he is an amazing mathematics man, I'm telling you. He knows numbers like there's nobody's business. So he's able to tell you what you should be investing your money in. So we're starting off with $32,000. After 5 years, we want to know how much more money am I going to have in there. That's if I never touch it, I just leave it alone. And The best kind of accounts you guys can find is the more frequently it's compounded, that means the more times they're giving you back the interest you've earned. So if you could find a compounded daily, that would be amazing. Doesn't usually exist. So this one says compounded quarterly. We'll talk about that keyword there in just a moment. So if you see what I did, I really marked up my text. Anytime I'm given a word problem, I always underline any of the main numbers that they give me, because those are going to be crucial to us finding our answers here. So this compound interest formula you also need for your midterm. This is the other formula. So we need the two from the last slide and this one from this slide. So here we go. Let's go over the letters. P is my initial investment. Again, I'm going to have my 1 plus r, but this time it's r divided by n. So this time there's like a little bit of a fraction in there. We'll talk about why in a minute. Raised to the nt. So P is the initial amount you're investing. R is still your rate of growth. T is still time. But this equation has a new variable. This one has an n. And what n is, it's the number of compounded periods. So we'll start plugging in numbers and we'll see if it all makes sense. So here we go. Our amount is going to equal, Anna, what do you think P is going to be? 32,000. Perfect. 32,000. 1 plus, Kayla, what does it say my rate is? What's my interest rate? 3%. Now in the last problem, was I allowed to put 3% there, or did I have to do something else to it? I have to move the decimal. Let's make 3% a decimal. So move it 2 times. So right now at 3%, I don't see a decimal. So some of you are like, how do I move the decimal? I don't see the decimal. If you had $3, where's your decimal at before we start? If you have $3, just after the 3. So I got to move it twice. 1, 2. So this is going to be 0.03.
We don't need to have one of those tops on it, basically like a line above it, where it's 3.
But this time we don't have to do that, Billy. So Billy's saying, don't I have to put a line over it saying it's 3.3333%? Nope, because that would only be if it was like 3.33333% to start with. Yeah, it would have to be that way to start with. Now n, it says, is my number of compounded periods. It gives it to us, but in a slightly different manner. It says compounded quarterly. So if here's your year, right, quarterly would mean how many times a year are they giving you that interest? Quarterly? 4. Good job. So your n is a 4. So they do give you the number, but it's hidden inside that word quarterly. So instead of an n, I'm going to put a 4. And then for my variable, I have 4 times t, or n times t. So 4 times, and how many years am I leaving it in there? 5. So that's kind of a crazy mess right now. So we're going to work it out one piece of the puzzle at a time. So in your calculator, can you guys first do, let me highlight it. Can you first do 0.03 divided by 4? We're going to go step by step so we don't make any mistakes. And then add 1 to that, because that's all inside parentheses. And did we get 1.0075? Yes? On the outside, I have a 4 times a 5, which is going to give me what? 20. Okay, so out of what I have left right here, who thinks they know what I would type in my calculator first? Which portion of my problem? What do we think? Because I can't do, not 32,000, right? Alex, what do you think? Yeah, I can't do the 32,000 first in my calculator. What parts do I need to do first, June?
You type in your constant, 1.0075, and then do the.
That's okay.
With the exponent.
Perfect job. So whenever you guys are using calculators, you have to do order of operations for your calculator. So we have to do the part to the exponent first. Always hit enter, and then do times 32,000. And let's see what you guys got. So we started with 32,000, so your amount should be more than 32,000, right? That's one way to gauge yourself. You're making interest on this money. We're not losing money here. And since we're talking money, think about what makes sense to round to. Because I know it gives you a lot of decimals in there, but we're talking money, so your answer needs to make sense.
To the second place.
Exactly. So Billy said to the second place because we're talking cents. Who's brave and wants to try their answer?
Just ask a question.
Sure, ask a question.
For the exponent outside the number 4 times 5.
This one? Yeah.
Yeah. Why would you multiply the 5 by 4?
My formula is n times t.
T.
Yeah, so I have to do my n times my t. So
So
yeah, the 4 times the 5. Good question. Anna, you want to try?
Sure. So that's $37,231.72.
Not quite. I think you hit enter one too many times. Anybody else want to try? Is that what you guys got to? What did you get?
37,157.
I got 35,157 and 89 cents. No? Let's pull up my calculator here. We're going to try. Okay, so, oh, and this one doesn't do exponents. That's awesome. So we're going to have to try it in a moment. But when I tried it, I got 35,157.89. That's what I got. Anybody get what I got? No? We all got different answers? That's a difficult one. But it shouldn't be if we have a calculator. All right, let me grab an iPad. I can at least use the calculator on the iPad. And this one doesn't have a calculator? Even better. Okay, somebody let me use their phone. And where's your calculator? Oh, there you go. Okay, so we're going to start with so did we do the 0.03 divided by 4 correctly? Yes, 0.0075. We're going to raise that to the 20th power and hit enter. And then we're timesing that by 32,000. That gave me a different answer too. Good grief, Charlie Brown. Yes. Yeah, so the correct way to do it is to add those two together first because they're in parentheses, and then the whole parenthesis gets raised to the 20th power. So I will try again, and I will post the right answer in the class by the end of today, once I have my real calculator. So that kind of just sums up at least how to set up your problem properly, but I'll make sure before you guys leave the room that we have that down. So for today, I'm asking that for your week 6 essential question that you resolve the last example that we just did, but I want to know the total after 8 years. So all you have to do is do the exact same problem we just did, but instead of your t being 5, your t would be 8. So you're going to try it again and put that answer for me into the Dropbox. So if you could give me your whole equation, this way I can make sure, even if you get the answer wrong, I can still give you points. So give me the whole equation, and then give me your total after 8 years. Yeah, I'm going to grab some. I'm going to grab some. All right, thanks, Carly. Have a great day. Okay, just to give the correct final answer on this slide, it was 37,157.89. So I apologize, I had the wrong number written in there. Thanks, guys. Have a great day.